you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T with a tutorial on statistics. This is part 3 of a 3-part series on probability and statistics for my Algebra 2 class. So let's get going. Statistics is a branch of math where we analyze and study data. So in processing the data, we need to gather it, organize it, analyze it, maybe present or represent it, and interpret it. One of the couple of the vocabulary words, population. If we talk about population of data, that would be all possible members of a particular subject or topic area. And frequently that could be a very large group of items or people. So frequently statisticians don't have time to, say, poll every voter in the US, for example, if the voting population was our statistical population. So they use samples, so they pick a subset of the population. There's a whole aspect of statistics in terms of how you select a sample, which we won't be getting into. So we need to, once we've collected our data, we have to organize it. Frequently when we are looking at some of the statistical measures, we will want them in order, and we could use a stem and leaf chart, which I'll show in a minute, to arrange numbers in order. We may also group the data together in intervals or clumps and represent them using pie charts or histograms, which is a type of bar chart. So here's some data that we'll be using in the tutorial here. These are some scores from a midterm exam, and we might want to organize them so we can, we could try to make a list and pull them out and put them in order. What we're trying to accomplish here is grouping and orders. So a stem and leaf chart has, normally the leaf is the last digit and the stem is the rest of the numbers. So our scores could go from 100 and the lowest score is 20 something. So the stems are 2 up to theoretically 10. And we write the leaf, the digit, on the line. So I do this in 2 paths. So in the first path, I just go through the numbers and write each number. So 82 would go here, 93 is this, 93, 57 is this, 57, and we go through the list in order. Now we want these in order, so now we've kind of grouped the numbers by tens, so now we can order each of these rows. And now we have a ordered stem and leaf plot. If we were going decreasing, this would be 90. Well, actually, decreasing would go right to left, so 95, 95, 93, 93, 93, etc. on down to 27, or counting from the bottom, we're going left to right, 27, 30, 42. So that's a stem and leaf plot. Now, if we group the grades that represent an A, B, C, D, and F, and count how many of the grades were in each category and plot them in a bar chart, that's called a histogram. So in this case there were 6 A's, looks like here, 8 B's, 4 C's, etc. And we could organize that same data as a pie chart. So the size of the wedge in the pie is the percentage of data. So there were 21% of the grades were A's, so that wedge would be 21% of the full circle. If we wanted to figure out how many degrees this would be 21% of a full circle, which would be 21% of 360 degrees if we were trying to use a protractor to sketch a accurate pie chart. These days, almost everybody's going to use some kind of spreadsheet program for producing these charts. Now, one of the key measures and the simplest measures on statistics are called measures of central tendency. This gives us a view of what how the data is clustered around what's called the mean. The mean is a numerical average of the data. So in ours we had 29 scores, so we add up the 29 scores and divide by 29. The median is different, but somewhat similar. The median is the middle value in the data. So since we had 29 numbers, we would be counting in 15 numbers from either end and arrive at a middle number. If we had had 30 scores, if we counted and found the middle of 30, it would be between two numbers. So the procedure is to take the number on each side of the middle and average those numbers. Again, we can use a stem and leaf chart to organize those and find, say, the median, and we can use the graphing calculator to calculate all of these items. We'll show that in a minute. Mode is the most frequently occurring value. So if we go back to our list, oops, wrong way. When we look here, we had, let's see, we had 3 of these, so 393s and 382s. So those would be the mode. When you have more than one mode, in this case 2 modes, that could be called bimodal. Some data may have no numbers repeated, so they may have no mode. And range is the distance between the minimum value in the list and the max. Now we can use the graphing calculator to calculate all but the mode. And to do that, let me bring over the calculator. You got some screen captures here, but let's look at how to do that. So let me pull up our data. So this was our data. Now the first step is to press the Stat button, and we want to input our data, so press Edit. And we want to enter our data into list 1. Now to save time in the video, I've already typed in or keyed in the 29 numbers for our data. So if we scroll to the bottom, we will see that there are 29 numbers in our list 1. So the last item here was 90. Once we have the data entered, to calculate those measures of central tendency and some other statistical measures, we're going to press the Stat button and go to Calc menu, the calculation menu, and these measures that we're doing, the measures of central tendency, are called one variable statistics, so we select that. That puts the command on our calculation screen and we press Enter. Now this is similar or the same thing as the screen I had captured here. Now in terms of nomenclature, in statistics, X with a bar over top of it stands for the mean, so our mean rounded was 70.8. If you added up all the values in the list, all those scores, it was 2053. The sigma, from, if you remember from a previous video, means summation. We're not going to use this. In a minute we'll talk about these two measures. These talk about what are called standard deviation, talks about how the data is dispersed. There were 29 items, N is the number of items. Now this arrow says there's more data, so let's scroll down. So we already had the mean, and now we have the min and the max. So we could subtract and calculate the distance for the range and the median. We'll talk in a minute about this Q1, Q3. Those are called quartiles. So enter your data into list 1, press Stat, and do one variable statistics. Now we talked about the range, which was the distance between the min and the max, but we may also want to break the data up into groups. A frequent one is to break it up into quartiles, meaning we're going to break the data up into fourths. So the first quartile is the score where 25% of the data is less than that number. The median is the middle, so that would also be Q2 for quartile 2. The third quartile is halfway between the max and the min. That's 75% of the data. And the max would be Q4. Each of these contain roughly the same number of data items, and they each contain 1/4 of the data. Now we can make what's called a box and whisker plot using that data to give a graphical representation of the spread of our data. Box and whisker plot looks like this. The box goes from Q2 to Q3. And this line in the middle is our median. And these points in the end are our min and max. So this is the box, and these are our whiskers. So this is the middle data. So our data on the above the median was a little bit more tightly collected or tightly dispersed, and on the bottom end we were more spread out. Now you can use the graphing calculator to do this. Now we can get these numbers for it to put on the number line here. The min is the 27 here, max is our 95, this boundary is Q3 85, 55.5 exact, and our median. You can also have the graphing calculator graph it. To do that, we have to turn on what's called stat plots. So I press the second key and y equals, and I have to turn my statistical plots on. So I'm going to press enter here and turn it on. And maybe have used scatter plots before, but now we can use this item here. Whoops, I skipped it. The fifth one over, that is a box and whisker plot, and we're going to draw the plot for the data in list 1, which is where we've put our data. Now, if I graph it at this point, I'm not going to see much because my x-axis needs to go from about 20-something up to 100. So I have to go into Window, and I need to set my x. So let's cover the scores that could be on the test, 0 to 100. And x scales tells where the tick marks will be, so let's set that every 10 units. And now let's press Graph. And again, we can see the box and whisker plot for our data. Again, we can see how spread out the data is. Sometimes we want a finer view of where data lies. Sometimes we use percentiles, or sometimes deciles, which would be every 10. So a percentile, whatever the number is the value in the table where that percentage of values are less than or equal to a particular number. So if we wanted to know what score would be the 90th percentile, there were 29 scores in the table, so 90% of 29 is approximately 26, so we would be looking in our ordered list of data the place where there would be 26 scores less than or equal to a particular number, and that came out to be 93 in our data. Again, you have to use your ordered list of numbers. So if we go back to our stem and leaf plot, we're looking for 26 numbers to be equal to or lower. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So this represents a 93. That's the 90th percentile, meaning 90% of the scores were equal to or less than that score. So if you were the one that 93, you did equal to or better than 90% of the people in the class. Another frequently used measure of the spread of the data is called standard deviation. It measures how the data is dispersed or how it's clustered. We use the symbol, the Greek letter sigma, to represent standard deviation, and that's for an entire population. Now we use this summation symbol in our last video. So that's what this is saying, is that we're going to take each point in the data, each data item, and subtract from it the mean. So we're finding the distance from the mean of every item and squaring that number, and adding all those distances up, and then dividing by n, and then taking the square root. If we were dealing with, say, a sample of a large population and we do not know the standard deviation of the whole population, we can calculate a sample standard deviation to estimate our population thing, and we use a similar formula, but we divide here by n minus 1. It gets into a topic of statistics called degrees of freedom. For today, we'll use this sigma. What's important is not so much how we calculate it, because we'll be using the graphing calculator to calculate that. So if I go back to my data, I can't go up, so let's just recalculate our data here, our stats. Again, for our test scores, it was about 19.6 was our standard deviation. Now, when we're dealing with large populations of data, well, first, before we do that, one of the things we have to deal with, so I just showed you how we calculated the sigma. We just showed that there. One of the things we have to deal with in statistics is something called outliers. Outliers are potentially anomalies. Maybe there was some error in the data collection. Maybe we recorded a number wrong. Or the data could be valid data and it's just a rare case. Statisticians, to avoid these outliers from significantly impacting the data, frequently a statistician will throw out the outliers. So instead of subjectively deciding on what's an outlier, mathematicians typically identify outliers as any data items that are more than 3 standard deviations away from the mean. Now, in our data, 3 standard deviations would be a little bit less than 60, and the mean was 70, so an outlier would have to be around 10. Now, our smallest score was 27, so based on this statistical definition, we would not have any outliers. So our last topic here in statistics is something that you've maybe seen called the bell curve, or it's also referred to as the normal distribution. On large amounts of data, when you collect it, frequently if you distributed the data using a histogram, we would get a shape that looks like this, where this is the mean. Many of you will be taking the SAT test soon, and when you're comparing the SAT scores for all the students in the entire U.S., if we plotted all those scores, it would have this shape, as well as if we were collecting the heights of all, say, the adult men, say white adult men in the United States, and plotted their heights, that would also have this shape. Now, if you notice on the bottom here, we've got the mu stands for here as the mean, so that's the mean of the data, and we've counted off adding 1 standard deviation, adding 2 standard deviations, adding 3 standard deviations to the right, and subtracting multiples of standard deviations to the left. And no matter what the data is, if it's normally distributed, these percentages in terms of the amount of data that's in each interval is always the same. So you can see here about 68% of the data is always within 1 standard deviation, either below by 1 or above by 1. If we go from 2 standard deviations, that's 95% of the data. So only about 2.5% of the data on each end, or 5% of the data, is more than 2 standard deviations away. When we do our outliers that are out here, we're talking about a very small percentage of the data. Again, very rare cases. It's around, this number is about 0.15 or something percent, so it's a small percentage of a percent. Now we could use that to make estimates. So let's say I already talked about this, let's say we know that the adult men in the U.S., by sampling or whatever, we've determined that the average or the mean height is 69 inches, and the standard deviation of that population is 2.75 inches. So if we wanted to know what percentage of men in the U.S. are 6 feet or taller, I've laid out here Here's our mean, 69, and then I've added 2.75, added another 2.75. So these are the boundaries on our percent curve. So 6 feet 72 inches, so that's around here. So men that are 6 feet or taller are out in this part of the curve. They are bigger than 1 standard deviation away from the mean. This percentage out here adds up to about 16%. If we wanted to know what percentage of men are shorter than about 63.5 inches, that's 2 standard deviations away. So out here, that's about 2.2, or on some tables, these percentages, that would be about 2.5%. So again, we can kind of get an idea of the distribution of our data. So I hope this helps, and good luck with analyzing data. You see data on the news all the time, polls back in the presidential election, and now there's all kinds of polls and surveys about the gun control legislation, immigration legislation, etc. And the statisticians that analyze that data are using these measurements. So have a great day.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready?